Okay, good morning. So we continue our topic of quadrilaterals. Might be many things that I am talking today is not related to quadrilaterals. I know that there are some problems left for us to solve, but if you don't mind, let us continue the lesson because this would be the last session before the break. Let us continue a little bit more, then we will have another session probably focused on solving problems. One problem, do you remember the last thing that I talked last time was the hinge theorem, and then we more covered the problem itself, that the theorem itself, and proved this. But I'd ask you to think about the converse, if the converse is also true or false. So what was the content of the hinge theorem itself, which was not related to quadrilaterals at all? It should have been covered when I was talking about triangles. So the point was that if I have two triangles, ABC, and then I have another triangle with two equal sides but a smaller angle between them. So for example, something like this. So what I mean, of course, by this, it's not very clear that it's the case. Let me make it more clear. Yeah, something like this. A prime, B prime, C prime. So if AB is equal to A prime, B prime, if AC is equal to A prime, C prime, so we know that AB is equal to A prime, B prime. We know that AC is equal to A prime, C prime. We know that the angle A is greater than angle A prime. So the hinge theorem actually told us that BC is also larger than B prime, C prime. So I talked about the converse, but actually that's not the converse. It might be that I was a little bit sloppy. I just want to see that if I can interchange the role of these two. So it's not the hinge theorem, it's not the converse, because the converse I have to replace to swap these two statements, but I'm not going to do that. My question is that if I give you AB is equal to A prime B prime, if I give you AC is equal to A prime C prime, but this time instead of telling you that the angle A is greater than the angle A prime, I tell you that the side BC is longer than the side BC prime, B prime C prime. Can you still conclude, okay, so the angle opposite to BC, which is A, should also be greater than the angle A prime, which is opposite to B prime C prime? At least intuitively, what do you think? The answer is a yes or a no?
Yes.
Yeah, I would probably say yes.
Yeah, it should be a yes. And then if I don't know, I didn't check the video. If I have talked about the converse, that is not the correct terminology, because you see that I haven't swapped this P and that Q. Okay.
Yes.
But do you think, how can we prove this? So, because I want to cover as much as I want, let me just tell you that we prove this by contradiction. Proof by contradiction. So my claim is that under these conditions, angle A should be larger than angle A prime. If you say no, assume that in contrary, that this is not the case. If you say that angle A is not larger, is not greater than angle A prime, then you have to admit there are two options left. Either angle A is equal to angle A prime, or angle A prime is greater than angle A. Yes? Now, can you tell me what are the consequences if this happens? For the first one, can you tell me what is the consequence?
They become congruent.
They become congruent because you are already telling me that this side is equal to that side, A prime, B prime is that, and then you are telling me that AC is also equal to A prime, C prime, and now suddenly you are telling that the angle between them are also the same. So this means by SAS axiom, SAS axiom, I can conclude that the triangle ABC is indeed congruent to triangle A prime, B prime, C prime. And when they are congruent, what can I conclude then?
BC should be.
Yeah, so it means that BC is equal to B prime, C prime, and this is in contradiction with my assumption. So I use this symbol to show the contradiction, yes? So it is a contradiction with my assumption. So if you tell me no, you have to accept either this is true or that is true. The first one cannot be true because it gives rise to a contradiction with what I have as my assumption. But what about this case? If angle A prime is larger than angle A,
Wait, what was the triangle inequality again?
no, it is everything you need is on the board.
By
Okay.
the original hinge theorem, that would.
Yeah, exactly. That's the hinge theorem again. Because you are giving me that these two sides are equal, but now you are telling me that the angle of the second triangle is larger than the angle of the first one. So according to the hinge theorem, I have to conclude that the side opposite to the bigger angle is bigger than the side opposite to the smaller angle. So it means that you have to accept that B prime C prime is larger than BC, but that's also contradiction, because you're telling me that BC is larger than B prime C prime. So you see that this is a nice trick. So that's also a good exercise in proof by contradiction method. Any questions? Okay, so that is something that you expected is indeed true. Okay, so today we will cover a lot of interesting material, but very simple. And mainly I want to somehow to keep them in your memory. They're extremely important. Simple ones. The first thing, which is very famous, is that if you have the median to the hypotenuse in a right-angled triangle, it has a very nice relation with its hypotenuse. So what I mean, assume that I have a right-angled triangle. Yes? This is my right-angled triangle, ABC. And what I do, I will draw the median corresponding to the hypotenuse. What I mean that I find the midpoint of BC, and I call it M, and I join A to M. Yes, that is the median corresponding to the hypotenuse in a right-angled triangle. We want to show that AM is half of the hypotenuse. So the point is to show this median, AM, is equal to 1/2 of BC. And the proof is very simple. The theorem itself is also statement itself is also very simple, but it is a very powerful tool. You need to have it in your memory. Okay, do you have any idea what to do?
Extend the median.
Yeah, so that is the good trick, yes? We extend the median to its size, to its length, so that I get, I don't know, the point A prime, is that good here? Yes. So based on my construction, I know that these two are the same. Yes? And I join it to, for example, C prime in this case. And if you want, I can also have it dotted line. But of course, what I know about BM and MC, I also know that they are equal in size because M is the midpoint. Okay? And then what happens? This angle M1 is equal to angle M2 because they are vertical. So this means that these two triangles are congruent. So if these two triangles are congruent based on SAS, yes, two sides and the angle between them from one triangle, two sides and the angle between them from the other triangle, they are the same. So these two triangles are congruent. So if they are congruent, what can I conclude? I can conclude that this one, this angle, let me call it C1, is equal to angle B. Yes. So I know that angle C1 is equal to angle B. I also know that the side A prime C prime, A prime C is equal to AB. Yes, so I know that this side is also equal to this side. Yes. Okay, so how can I conclude now? So what is the conclusion when I have C1 I think C1 is not useful. So let me change it. B equals to C. So I want to conclude that A prime is equal to this angle, A1. That is A1, A prime is equal to A1. Of course, that was not wrong, but that is not something useful because I want to show that these two lines are parallel. Yes? And now, can I conclude they are parallel? Because now you see that you have a Z shape here. And then you know this angle is equal to that angle. So it means that your Z shape is actually correct. So this means that AB is parallel to A prime C prime. A prime C. Yes? So I now know that AB is parallel to A prime C. I also know that AB is equal to A prime C. So these two line segments are not only parallel, but also equal in size. So what can I conclude about the quadrilateral AC prime B? So if I complete it in my head, if I complete this quadrilateral in my head, what type of quadrilateral is this based on what we learned before?
Parallelogram.
It's a parallelogram. So if you remember, the definition of the parallelogram is to prove these two are parallel, these two are parallel. But we also learned that if I just show that two of them are parallel and opposite and equal in size, then I can guarantee that my quadrilateral is indeed a parallelogram. So this means that A, B, A prime, C is a parallelogram. Yes? But more than that, it's a better parallelogram.
Yeah, because it has a right angle.
It has one right angle from the beginning. So it is a rectangle. Yes? So this means that, and since the whole angle BAC is 90 degrees, this means that A prime C is a rectangle. Okay, and then one of the properties of a rectangle is what?
The diagonals
Are equal in size. So this means that the diagonals A prime is equal to BC. But based on my construction, what is the relation between A prime and the original blue line AM? A prime is double in size, yes? So this means that instead of A prime, I can write 2AM, and this becomes BC, and then I can conclude that AM is 1/2 BC. Extremely simple, but very handy. So remember it, memorize it. Yeah, I shouldn't try to say memorize. After understanding, it's one thing that you need to have it in your memory. Okay, so what I want you to have it in memory, in your memory, that's also good. See, you can have this picture in your head somewhere. So you see, if this is a right angle triangle, so let me just draw it with red, and I really don't think I'll try. Yes, so this is a right angle triangle. You draw the median. If you draw the median, remember that this and that are all equal. Yes? So remember, these three lines, if that's a right angle triangle, they are equal in size. So it means that you partition the right angle triangle into two isosceles triangles. So I have one isosceles triangle here. I have another isosceles triangle here. So this means automatically you need to have these things in mind. If this is alpha, this is also alpha. If that is beta, that's also beta. Yes? Okay, so for example, do you know, I don't know if you have it in mind, so sine of 30 degrees is 1/2. Okay, so let us see if we can prove this using this idea. So if you want to prove this, I need a triangle, a right angle triangle with angle 30 degrees. So for example, I will draw a right angle triangle so that one acute angle is 30 degrees. And then of course, if I ask you what is the definition of sine, you remember from trigonometry that sine is the opposite side, which is AB in this case, divided by BC.
Oh.
Yes, if I can somehow find this ratio, I am done. But what can I do, even though it is not related to the median, but no one prevents me from drawing the median. So I will draw the median, but when I draw the median, if this is 30, that is also what? So I need to find the relation. So sine of AB, okay, so if this is 30, this is 60. We know that. And because we just showed that these two are equal, if this is 60, that is also 60. But then suddenly what happens? This is isosceles. Two of them are 60. It is also 60. So this means this triangle for this particular case is not only an isosceles triangle, but an equilateral triangle. So this means that AB is equal to BM. So AB is equal to BM. So I go here and instead of AB, I can put AM and I divide it by BC. Sorry, BM. So, but what is BM? BM is half of BC because M is the midpoint. And this expression becomes 1/2. Yes? Okay, let me, just for practice, let me give you another problem. That's also interesting. So assume that you have a right angle triangle with one angle to be 15 degrees. So this angle, assume that it is 15 degrees. So let me write it A, B, C. Now what I do, I draw the altitude corresponding to the hypotenuse. So for example, I drop a vertical line from A to this. And let me call it AH, and I will call the length to be H. Or I don't need to call it, okay? Now we want to prove that the length of AH is a quarter of the hypotenuse. So of course this is very exaggerated. I don't know if that's correct or not. But the claim is this. We want to show that AH is 1/4 of BC. So this tells you that if in a right angle triangle one acute angle is 30, the side opposite to the angle 30 is half of the hypotenuse. This is good to remember. Of course, this is not something that you will forget. But this one is probably not very famous. So if I have a right angle triangle, so that one acute angle is 15 degrees, I want to show that the altitude corresponding to the hypotenuse is a quarter of the hypotenuse. I would recommend you to think at least a little bit about it so that we can continue. I just want to pause the video for some minutes. Any ideas? Just as an example, of course, this might be hard if you didn't know about that theorem right away. So I'm giving this example because of that theorem. So you need to draw the median yourself. Okay? So in the problem, you would say that, okay, we draw the median to the hypotenuse, AM. It's not the way of doing this. Okay, so that is AM. But then let us see what happens. It shows that it's not a very good picture because I hope that you agree that this and that should be the same based on what I learned, yes? So if this is 15, that's also 15.
Mm-hmm.
But what is this one?
That's 30.
Why?
Because the others are 75 and...
Or, better, I still insist you to see that this is an exterior angle. So if that's an exterior angle for this triangle, it should be the sum of these two. And if this is 15 and that's 15, this has to be 30. Yes? And now look, this happens, you see here, this is a right angle triangle, do you agree?
Yeah. Oh, wait, actually, I found this.
And this is 30, so the opposite side should be half of the hypotenuse. But this one is also half of this hypotenuse, so that's a quarter, yes? So I would say that this is 30 according to what I showed here just right now because of sine of 30 or something. So AH is equal to half of this hypotenuse, which is for this triangle, AHM. So it becomes 1/2 AM. But if I ask you, what is AM? AM is half of BC itself. You see, it was extremely simple, yes? Okay, now another question is somehow the converse is also true. If I have a median of a triangle is equal to half of the corresponding side, can you conclude that the triangle is indeed right angle triangle? So the question is this. I draw a triangle, still I don't know if it is right angled triangle or not, but I know something. I know that if I find the middle point and I draw AM, so what I know, M is the midpoint, more I know that AM is half of BC. Can I conclude that the angle A is 90? So that's also if that is true, this is indeed the converse. So in the theorem itself, I assume that A is 90, I concluded that AM is equal to 1/2 BC, but here I know that AM is half BC, and I want to see if that is true, that A is 90. If you think that's true, you have to prove it. If you think it's false, you have to show me by a counterexample drawing a picture to motivate me that's wrong. So what is your opinion about it? Do you think it's true or false?
We prove the converse of the pentagon, that if the diagonals are equal, it's a rectangle. Did we prove that in the last lesson?
Yes.
Yes. So
We showed that if the diagonals bisect, then the original quadrilateral is a parallelogram.
Yeah, but can we also prove that if they're equal, it's a pentagon? It's a rectangle.
Yeah, we can check that. We didn't state it, but I think that's also true, yes?
Yeah, I mean, okay, because if we did prove that, I mean, you
Well, we
just-
haven't proved that formally, so if you
Okay.
want, you can just mention how we should do it here.
well, if we just extended the,
Extend again the same trick.
yeah,
So I extend it
and then
to
this,
some point A prime, then
and
what?
then you make a quadrilateral. Just,
So you just say that I draw this one and that one, yes?
yeah, and then if you know that these two diagonals.
So we know that this one is equal to that one.
Yeah, but-
According to my construction, I also, by the way, I forgot to put this here
Yeah,
as well. Because I know that AM is 1/2 BC. So I know these things, and then this means that this is also the same.
Yeah, so the diagonals are equal, but I don't know if you prove that this would mean it's a rectangle. But then we would prove that.
Yes, we can prove that then. So what do you say?
How to prove that this is pentagon? This is a rectangle.
Yeah, so if you want, you should. So because if you prove that this is a rectangle, you are done, yes?
Yes.
Okay. So how can we prove this then? Okay, you can think a little bit. I would say that shouldn't be hard to prove that this is a rectangle, of course. But do we really need to do this or not?
I think so.
I
there was
think
just
there
one
is a
original-
better way to do it.
Probably.
Very simple way.
Yes, I think.
Just playing with angles. Yes? So what I do, if you don't mind, let me just clean this. We don't need it. But we know that these are isosceles triangles. So let me call this alpha. This is also alpha.
On the report.
Isn't it simple?
Yes.
If this is beta, that's also beta.
Yeah.
But look at the original triangle. The sum of all angles, alpha plus beta, this angle, plus this angle, plus that angle, should be 180, yes?
Yes.
So this is 2 alpha plus 2 beta is 180. And I divide everything by 2, so alpha plus beta is 90. But alpha plus beta is that angle. Yes? So I would say that is a simple way for this case, but that's also a different problem that you actually brought up. And if the diagonals are the same, can we conclude that a parallelogram is indeed a rectangle? And I think we can definitely prove that. Okay. There is a very nice theorem about altitudes of a triangle. Yes? So by the way, what is an altitude? Height. Sometimes they call it height, but height is the length in principle. Altitude is the line segment. So it means that if I have a triangle, this is a very nice theorem, I would say. ABC. If I drop a perpendicular line from a vertex to its opposite side, this is called altitude, yes? Altitude. And the length of this altitude is height. How many altitudes you can imagine for a triangle? 3. But again, the question is that, do you remember we talked about perpendicular bisectors? They were concurrent. And what was the name of the point of concurrency to refresh your memory?
The incenter?
No.
That's the what was the
Circumcenter.
circumcenter.
Why it is called circumcenter?
Because this
It would be the center of a circle
yeah,
that will pass
passes
through all the points of all vertices of the triangle. And then we had another theorem. If we draw 3 angle bisectors, they will also be concurrent. And the point of concurrency is
the incenter.
incenter. Usually the circumcenter is denoted by O, the incenter is denoted by H. And then, if you don't mind, because we will also have another center today, let me change this one to some other name. And then, if I draw another altitude, then the interesting thing that will happen is that the third one will also pass through the intersection of these two. Okay? But the proof of the previous ones were actually not that hard. If you go and I hope that you all have this in your memory now. But if you don't, you can go and watch the video. So proving that perpendicular bisectors are concurrent, the angle bisectors are concurrent, are not that hard. At least you don't need to be that creative. But this one is called orthocenter, and that is denoted by H. So orthocenter. If someone asks what is orthocenter, you would say that that is the point of concurrency of the altitudes of a triangle. Of course, in Mathematics Olympiad, we will study the properties of this H later, but not right now. I just want to prove that this is indeed the case. But I want to draw your attention to particular triangles. So for a right angle triangle, what will be the orthocenter? Can you tell me?
It would be the A.
A. A itself will be the orthocenter, yes? Because this would be the altitude for AB. This would be the altitude for AC. And of course, the altitude of BC also passes through here. So in that case, the orthocenter is actually exactly equal to the right-angled vertex. But we also have another scenario. What happens if I have an obtuse angle? I have an obtuse triangle. For example, so let me just write here. So in principle, the theorem that I am going to prove that these are concurrent, I don't need to be worried about the right angle triangle. The right angle triangle case, in that case, they are already concurrent. And the point of concurrency is exactly this vertex. So there are two main things left for me. I need to show for scaling triangles, which are acute triangles, all the angles are acute, and then at least one angle is obtuse, yes? So if this happens, if I have this scenario, let us see where, if any, is the orthocenter here in this case. So this is, by the way, a definition. If I ask you to draw the height or the altitude of this vertex, so you just draw this perpendicular line. This is one of the heights. So if I ask you measure another height or draw another altitude, so you need to understand that you need to continue, extend this, and this would be another one. Okay, so this is, by definition, is called the height. So in principle, if I ask you what is the height is the distance from a point, from a vertex to the opposite side. That is called the height. And then this line segment is called the element. And then what happens for the next one? If I want to draw for this one, I have to extend the line from this side and draw another one. And if I draw them perfectly fine, then they will continue and be concurrent. So that would be orthocenter in that case. Okay, so this is a difference. So the orthocenter of an acute triangle is interior to the triangle, but the orthocenter of an obtuse triangle is outside. And for the right angle triangle is exactly this vertex. Okay. But now let us try to prove it for this case at least. We want to prove, the proof is elementary but very nice, I would say. So do you have any idea before I start how to prove? Again, we say that two of them will intersect at a point. We want to show that the third one will also passes through that point. Okay. let me just draw any acute triangle, ABC, and I want to show that the altitudes are concurrent. The proof is based on this. You, by intelligence somehow, draw another triangle in a way that the heights of this triangle become the perpendicular bisectors of the new triangle. And we have already shown that the perpendicular bisectors are concurrent, and we are done. Is the logic clear? So I want to prove that the heights, the altitudes are concurrent. I need to be creative. I'm just copying the proof. So to draw another triangle and prove that every altitude of this triangle becomes a perpendicular bisector of that new triangle. And we have already shown that the perpendicular bisectors of any triangle are concurrent, so this means that I am done. Is the logic clear? But the idea is this. How should I do that? Let me just concentrate on one of the altitudes. So let me just draw this altitude and call it AM. But now I want to construct my new triangle based on what I told you. You go from A, draw a line parallel to BC. Okay? So you see that this is under the title of quadrilaterals. So quadrilaterals will play an important role here. And I will do the same thing from point B. I draw another line parallel to AC. So hopefully I can do it here. Yes? And I will do the same thing from point C. I draw another line parallel to this one. Then I have a new triangle, A prime, B prime, C prime. It's a very, very bad shape now I can see from outside. Okay, but I hope that you are not fooled with my bad shape. The claim is that AM is perpendicular bisector to B prime, C prime, which is a very, very poor picture, yes. In principle, this length should be equal to this length, if you do it perfectly fine. But if I want to show that AM is the perpendicular bisector for B prime, C prime, I have to show two things. I have to convince me that AM is perpendicular to it, and I have to convince myself that A is the midpoint of B prime, C prime. Both of them are very simple now. The first one is even simpler. Why do you think AM should be perpendicular to B prime, C prime?
Because B prime, C prime is parallel
Yes,
to...
I just draw this new dotted line parallel to BC, and I know that this altitude is perpendicular to BC, so it also remains perpendicular to this line. So yeah, this part is really simple and done. So this angle is 90. No doubt about it. But why do you think AC prime is equal to AB prime? I emphasize again, the lesson today is also about quadrilaterals. So why AC prime is equal to AB prime? Yeah, I know this is a very poor shape, might be you're confused, but just follow the logic. For example, can you tell me what type of quadrilateral is this one and why?
It's a parallelogram.
It's a parallelogram. Why? Because I drew this one parallel to this one, and this one parallel to this one. So based on definition of a parallelogram, it's a parallelogram. So what does it mean? It means AB prime is equal in size to BC. So this means that this one is equal to this one. Now can you see the last one?
It's also a parallelogram.
Yeah, this one is also a parallelogram. Yes? Because this is parallel to this one, this is parallel to this one. So this means AC prime is also equal to BC. As simple as that. So this one is also equal to that. So what does it mean? It means that when I draw an altitude, this altitude is an altitude for the original triangle, but for the new triangle, it's a perpendicular bisector. And I hope that you agree that if I draw another height here, another altitude here, it becomes perpendicular bisector of this one with the same kind of reasoning, and then the same thing happens with that one. So it means that when I draw the altitudes, I have actually drawn the perpendicular bisectors of this new triangle. And it means that that is the point of, so this means that the altitudes are actually concurrent. Is there any question here? But what do you think will happen in that scenario? Can we also follow the same kind of things? Or this will be affected somehow? I don't think it will be affected. So in that case, probably we should be able to do more or less the same thing. Let us see how this will go. So in that case, if I take this one and draw a line parallel to that, so I hope that I am not making this picture very complicated. So I take this one, and then I will take this one and draw something parallel to that one. Yes. And then I take this one and I draw parallel to this one. I don't know why this is not writing. Anyway, so that would be your new scenario. This would be your triangle. But I think you agree with me that the same method will work, yes? Do you agree? Because now this one is a parallelogram. So this means this side is equal to that side. But what is the next parallelogram? I want to show that this one is also equal to this one. So if you are not confused, this one and this one and this one and this one is also a parallelogram. So this means that this one is also equal to that one, so they are equal. Yes.
But all of these triangles, by the way, they're similar, right?
Similar, or you mean congruent?
Are they congruent?
Which triangles?
Everyone. All of the before ones.
Yes, they are congruent. This one, and that.
Yeah.
Actually, that was one of the. But we haven't reached why.
Okay.
We will prove why they are congruent if we have time today. But I hope that you agree, nothing will change. The proof will remain the same here.
Yeah.
And by the way, that is important to remember that if you have an obtuse triangle, then the circumcenter is also outside. This is also comparable. Okay, so this theorem is also done. So we know that perpendicular bisectors, angle bisectors, and altitudes are concurrent. What is left? Because if I have a triangle, I have three sets of segments. One set of segment is the altitudes, one set of segments are angle bisectors, and one set of lines are perpendicular bisectors. There is only one set of lines left, set of line segments left for a triangle. Medians. And that is the most tricky one. We want to show that the medians are also concurrent, and it has a very, very nice property. We want to explore that. Okay, but before exploring that, so the idea is this: we want to pave the way to be able to show that the medians of any triangle are also concurrent. But before that, I want to give you two theorems. They are very important in their own, actually, and I will call them the same thing, the Midpoint Theorem, version 1, version 2. Okay, Okay, so what is midpoint theorem? Extremely important, very handy theorem. So midpoint theorem number one. It is not about a quadrilateral, it's again about a triangle. So what is the midpoint theorem? So if you don't mind, instead of writing it in words, let me just tell you what does it mean. So I have a triangle ABC. I pick the midpoint of AB, for example, and I call it M. I pick the midpoint of another one, for example, say AC, and I call it N. So what I know this length is equal to this length. I know this length is equal to that length. Yes? What I do, I just join the midpoints. Okay? But very interesting property will happen. I just join the midpoints. Then the blue line segment is definitely parallel to the third one. Moreover, the length of that is half of the length of this one. So it's very important. So this is the first version of midpoint theorem. It's a very simple theorem but very handy. So you just connect the midpoints of two sides, you get a line segment. The claim is this. So if I want to write this, I know that AM is equal to MB. I know that AN is equal to NC. And I want to show that MN is parallel to BC. And not only parallel, and MN is half of BC. So I want to prove that this is indeed the case. Yes? So remember, please send these theorems to your memory. They are extremely important ones. Okay, so this is a theorem for triangles, but the method that I want to use to prove it, one method is based on quadrilaterals. So what we do, you need to tell that you extend Mn to its own length. Yes? So you get point M prime. So what I know is that whatever this length is, which I don't know, is equal to this one by my construction. And then I join M prime to C. Now you immediately realize a quadrilateral appears. Okay, what is the type of that quadrilateral in general? The quadrilateral M prime, C, B.
Parallelogram.
Intuitively, it seems to be parallelogram, but we have to prove that. Why this is a parallelogram?
So the side, so M prime is equal to BC by construction, right?
So what is your strategy? The strategy is to show this small triangle here and that triangle are congruent. But are they?
Yes, because
everything is clear, yes? Because this side is equal to that side, this side is equal to that side, and these two angles are vertical angles, yes? So it means that if I call this one N1 and if I call this one N2, then these two triangles are congruent based on SAS, yes? So let me just write that. So triangle AMN is congruent to triangle CM prime N by SAS axiom, yes? And if they are congruent, I can conclude two things. I can conclude that M prime C is equal in size to AM, yes? But on the other hand, I know that AM was equal to MB from the beginning. So what can I conclude from here? I can conclude that M prime C is equal to MB. Yes? So now I know that I can put another dash on it. So these two are now equal in size. But they are also parallel. Why is that? Because when this triangle is congruent to this triangle, so this angle is equal to that angle. And then this means that I have my Z shape, yes? So this means that another consequence of that is angle AMN is equal to angle NM prime C. So this means that AM is parallel to M prime C. Yes? AM is parallel to M prime C. Yes? And then what happens? This quadrilateral becomes what? Becomes a quadrilateral, a parallelogram. Yes? Is that right? Because these two sides are not only equal, but also parallel. So this means that my triangle AMN is congruent to sorry. Yeah, they are disturbing me here. So here what happens now? Quadrilateral M prime CB is a parallelogram. Yes? And if it is a parallelogram, I am done. Because if that's a parallelogram, this blue line segment is part of this longer one. And this longer one is definitely parallel to this one because it's parallelogram. But moreover, MM prime is equal in size to MC. So this means that MN is parallel to BC, but also means that MM prime is equal to BC. But MM prime is 2 times larger than the blue one. Then I am done. So this means that 2 MN is equal to BC. So this means that MN is half of the BC. Yes? So you see that you see that this was a theorem in triangles, but we were able to prove it using the ideas from quadrilaterals.
Do you use medians to prove it?
No, but I will use this to prove the theorems for medians later.
But my initial idea was to draw the median of BC.
Okay, I don't know if that works. I should be able to hear you. So you say that if you take the midpoint here and the midpoint here and you connect them, so what you have this equal to that, you have this equal to this, but now you are telling me draw this median.
Yeah, I thought.
Okay, so if you think in that median, okay, I want to hear from you. So let me call it another P, for
No, I
example.
didn't really do much with that. It just seemed potentially useful. I don't.
No, so this is the proof that I have right now in my head.
Yeah.
But might be if you can find another way. Of course, we can prove it later in a more general context.
Yes.
But I want this version of it, which is probably the most important version, later. Okay? So you can also think about it. Might be you can have another idea to prove it. But that is called the first version of midpoint theorem. So let me just write midpoint theorem 2. In this midpoint theorem 2, I have only one of them is the midpoint. So the logic is a little bit different. So I know M is in the middle. But I do not choose the middle point here and connect them. I will draw a parallel line from M to BC. The claim is that, so what I do, this time, I know that AM is equal to MB. MN is just parallel to BC. This is what I know. I don't know if N is the midpoint. But I want to show that yes, N is also the midpoint. So this means that AN is equal to NC. I have to convince you about this. And of course, if AN is NC, by the first version, I can also claim that Mn is half of BC. Yes? So you see the picture is very similar to the previous one, but the assumptions are different. So I know AM is equal to MB, I know MN is parallel. I want to show that the second point is also in the midpoint. And if that is the midpoint, then according to the midpoint theorem number 1, I can also conclude that the length is also half of that. So how can I prove this? This is proof by contradiction. Okay? So how? I am claiming that n is the midpoint. If you don't believe in that, okay, so then it means you believe that the midpoint is somewhere else. So let me just, I don't write them, but I want you to understand. If you agree with me that n is the midpoint, we are done. If you don't agree, then it means that you need to show me where the midpoint is. For example, you might show that no, n prime is the midpoint. But why this is contradiction, can you tell me?
Would be parallel.
The idea is proof by contradiction. If you agree with me, we are done. If you don't agree, just show me the midpoint, because there should be some midpoint. So if that's the midpoint, we will immediately come to a contradiction.
Well, n prime isn't going to be parallel.
Yes, because of the first version. So what you do, you say that if you don't believe in that, so that is your midpoint, so then you draw this line. But now you know that AM is equal to MB from the beginning. You are telling me that n prime is the midpoint of AC, so it means that AN prime is equal to n prime C. By the midpoint theorem number 1, midpoint theorem number 1, I can conclude that Mn prime is parallel to BC. Yes? But that is contradiction, because on the other hand, you are telling me that Mn is parallel to BC. So this means that from this point M, I was able to draw two parallel lines to the same line BC, which is in contradiction with the parallel axiom. So this is done. Is that right? So these two versions are extremely important and simple ones that I want you to have in mind. Of course, my main goal is to use these theorems for proving the concurrency of medians. But they're also very interesting in their own rights. So let me just give you some examples before passing on. It's a very nice theorem. Not theorem, that's a very nice statement, but I mean that in mathematics Olympiad you need to have a lot of things in your memory so to be able to act fast. So one thing is very nice and very generic. If you draw a random quadrilateral here for me, let us for the time being keep the convex one. So I just draw a random quadrilateral here. I will try to make it very random, I don't know. Is that a very random one? It's getting close to a trapezoid now, I don't know. Okay, so yeah, just imagine that's a random quadrilateral. So I call it ABC D. Now I take the midpoints of all these sides and connect them. I will get another quadrilateral. But independent of what is the shape of this quadrilateral, that quadrilateral that I generate is always a parallelogram. Yes? So this means that I take the midpoint here, I take the midpoint here, so let me be a little bit more careful. So this one is equal to that one, this one is equal to that one, and I will take another one here, this one is equal to that one, and then I have another one here. This one is equal to that one. So then I call them M, for example, N, P, Q. Regardless of the original parallelogram, quadrilateral, this one that I generated right now is always a parallelogram. Or of course the special cases, rectangles, rhombuses, squares and things like that. But is the question clear?
Yeah.
Okay. Why do you think it should be the case?
If we draw the diagonals.
Yeah.
then
That's
the
the
midpoint
trick.
formula.
Exactly. So, for example, you don't need to draw, by the way, two of them. One of them will be enough. For example, let me just draw this one. So you will tell me that I draw this diagonal. And then I am done. Why? Because now I have a triangle here, I can use the first version of midpoint theorem. This point is in the middle. This point is also in the middle. Look at this triangle here. I am connecting the midpoints. So what can I conclude? I can conclude immediately that MN is parallel to BC. Moreover, MN is equal to half of BC. Yes? Now, forget about the upper triangle. Concentrate on the lower triangle. Again, I have the same scenario. I have two sides. I am connecting the midpoints. The line segment generated in this way is parallel to the third side. So it means QP is parallel to DP. But more than that, DB, more than that is that QP is equal to, I don't know why I wrote BC and you didn't complain. So BC was wrong, yes? It is BD.
BT.
Or DB, okay. Yes, sorry. I am just connecting the midpoint, so this line segment is parallel to the third one and half of it. And the same happens for QP. It's parallel to DP and half of it. If you compare this one and that one, both of them are parallel to the same line, so they have to be parallel themselves. So MN is parallel to QP. Moreover, both of them are half of DB, so they have to also be equal in size. So this means that this and that are not only parallel, but they are of the same size. So this means that this quadrilateral is a parallelogram.
And all the information you need for this is that you have a triangle with the midpoints of two sides.
Exactly. So that is extremely handy theorem. Okay, another one is also interesting to know by heart is something about a trapezoid. Okay, I want you to have it in your memory as well. Okay, so what can I do? This is the problem. I have any trapezoid that you like. So trapezoid, you remember? The constraint is that I have to have two parallel sides. So let me just draw this one. A, B, C, D. This time, this is more interesting. I join the midpoints of these sides. So I take the midpoint here. So this side is equal to that side. Let me call it M. And I will take the midpoint here. This means that this is equal to that, and I call it N.
That it's A, B, and then C is that?
Ah, yes, thank you very much. Yeah. This is not standard way. Of course, that will be read A, B, D, C, but let us keep this down. Thank you. But the point is that what happens if I connect these two midpoints? So I am choosing the midpoints of non-parallel pair. Yes, and I am connecting the midpoints of those. That is interesting. MN also remains parallel to those sides. So the claim is this, that we know that MA is equal to MD. We know that NB is equal to NC. the claim is that MN is parallel to BC, to AB, and of course parallel to DC, because AB and DC are already parallel. But interestingly, we can say something about the length. The length, MN, is the average of these two sides. So this becomes 1/2 of AB plus DC. So this is our question mark here. Yes? So why this is true now? Yeah, I made it so big, I will be in trouble soon, but yeah. The point is this. Let me see if I can do it the other way around. Yeah, but let me just do this. Okay, I extend this side to its own length. Yeah, so if you don't mind, you know what I am going to prove. So if you don't mind, let me clean this. Okay, so what I do, I extend this side to its own length. Not to its own length, let me think a little bit. Okay, so probably I am completely, because I need to know what I'm supposed to do. No, this is not to its length. I just extend it, okay? But then what I do, I would just join this point to that point and continue. Yes? So I just extend it, and then I just join this point to that point, and I continue until it reaches to point D prime. So I don't need the rest. So based on my construction, I don't know anything about the equality of these things, but I will show it. So the logic was just to extend DC and then connect A to N and continue it so that you get an intersection point, call it D prime. Yes? Now, I hope that this is now clear what is my strategy. You have this big triangle, and I know M is the midpoint, and I know that N is the midpoint. So what can I conclude?
The midpoint should.
So Mn is parallel to D prime.
Yes.
So one part is finished, that's it, just by drawing.
But don't we need to know that N equals NB?
Yes, you are right. You are right. So I have to prove that these two orange lines are the same. But that's also true. Why is that true? Consider here and here.
They're congruent.
They are congruent. Why that is true?
It's,
Why these are congruent, by the way?
it's angle
So one angle
side.
and this angle,
Is it angle side angle?
angle, side angle. Yes, exactly. So this angle and that angle are the same. So if I call it N1 and N2, so you know that angle N1 is equal to angle N2. But what more do I have? What angle you mentioned actually, hopefully you agree with me, this angle here is equal to that angle there because I have a stretched SZ shape, yes?
Yes.
This is parallel to this one. We know in a trapezoid this happens. So this means that I have a Z shape. So this means that this angle is also equal to that angle. Yes? So let me call it B1 and C1. So this means that angle B1 is also equal to angle C1. But I know that the side between these two angles, which is BN, is also equal to what? NC. So this means that these two triangles are indeed congruent. So ABN triangle is congruent to triangle NCD prime. And if they are congruent, now we are on the safe side. AN is equal in size to ND prime. Yes? So this means that I knew N was the midpoint of BC, but now I also know that N is the midpoint of this long orange line. Yes? So then you can consider this big triangle. By big triangle, I mean triangle ADD prime. What can I say? I can say that M is the midpoint of AD. And I know that N is the midpoint of BC. So the midpoint theorem version 1, tells me that MN is parallel to DC, to DD prime, which of course means MN is parallel to DC and is parallel to AB. But more than that, I can also understand that the length MN is half of the length of DD prime. Agree? Agree or not? So MN is half of the length of the third side, DD prime. But DD prime is AB plus DC. Why is that? Because, so this means that I realize that MN is 1/2 DD prime. So this means 1/2. Instead of DD prime in the shape, you see, I can write it DC plus CD prime. But what is CD prime?
AB.
It's AB. Because I showed that these two triangles are congruent, so this means that the third side here and this third side are the same. So this means that instead of that, I can write 1/2 DC. Instead of CD prime, I can write what? I can write AB. Yes? This is also extremely important to remember. I just write one problem for the next time, and then we end up the lesson. So the problem is again about the trapezoid, but let me write it in words so that you can draw the picture yourself. You need to understand the words, okay, in the sentence to draw the correct picture. So the problem is this. Prove that the line segments joining the midpoints of the diagonals of a trapezoid is parallel to the parallel sides yes, and equal to half their difference. Yes. So I intentionally wrote it in words. So you need to read it and understand what it tells you, and then try to solve the problem. So this time I want to connect the midpoints of the diagonals of any given trapezoid. Okay, no questions? So next time I will also continue. Okay, so next time will be after this Easter. Okay, so let us see how it goes. Thank you.